Have you ever been out on the water, looked at the endless ocean and thought, there is so much water here, but I can't drink a single drop? It's a huge problem for any ship on a long voyage. Well, the solution is just brilliant. It's like engineers managed to take the planet's entire rain cycle and shrink it down to fit inside a box in the engine room. So, before we get into the clever how, we've got to understand the why. And the whole problem really boils down to one simple fact. For any ship out there on a long haul, it's basically an island. I mean, really think about it. A modern ship is like a floating city, a completely self-sufficient world. But it's surrounded by trillions of gallons of water that are totally undrinkable. And you need fresh water for everything, for the crew to drink, for cooking, even for the machinery to run properly. So are you going to carry it all from port? No way! It's incredibly heavy and it takes up way too much valuable space. The only real solution is to make your own. So how do you solve a problem that big? Well, the cool part is marine engineers didn't have to invent a solution from scratch. They just looked up. Because, as it turns out, nature has been running the world's largest, most efficient desalination plant for billions of years. Yeah, it's the good old water cycle. It's a process we all learned in school, and it is beautifully simple. The sun heats up the ocean, which causes fresh water to evaporate, leaving all the salt and other minerals behind. This pure water vapor rises, it cools down, and then it condenses into clouds. And eventually, those clouds release fresh, pure rainwater. And that gives us the two key principles we need: evaporation and condensation. Now, the scientific name for this process is distillation. And all it really means is separating stuff by boiling a liquid to turn it into a vapor, and then cooling that vapor back down into a purified liquid. That right there, that's the blueprint. Okay, so now for the real challenge. How in the world do you take this massive planetary scale process and shrink it down to fit inside the cramped engine room of a ship? Here's the big roadblock. At sea level, we all know water boils at 100 degrees Celsius. Now, a ship's engine produces a ton of free waste heat from its cooling system. The problem? That heat is only about 75 to 85 degrees. See the gap? We just don't have enough heat to get the seawater to a boil. This is the central riddle, isn't it? How do you make water boil when you physically can't turn up the temperature enough? It seems totally impossible, right? Well, the solution isn't about brute force. It's about being clever. The secret isn't about adding more heat. It's about changing the physics of the environment itself. You see, the boiling point of water isn't fixed. It's tied to pressure. At our normal atmospheric pressure, it's 100 degrees. But what happens if you start sucking the air out of a sealed chamber? You create a vacuum, and the pressure drops. And as that pressure plummets, so does the temperature needed to boil water. In a strong enough vacuum, water will boil at temperatures as low as 70 degrees Celsius, a perfect match for the engine's free waste heat. It's that classic engineering saying, if you can't raise the bridge, you lower the river. Instead of struggling to find more heat that they didn't have, they just changed the rules of the game by lowering the boiling point. It's an absolutely elegant solution. So, we've got the principle down. Now let's see how the actual machine, called a freshwater generator, puts this incredible physics trick to work. The freshwater generator, or FWG for short, is really a perfect little mechanical version of the Earth's water cycle. The engine's waste heat acts as the sun, providing the energy for evaporation, and a set of tubes cooled by seawater, those are the clouds, where the condensation happens. The whole thing is a continuous loop that's actually pretty simple. You've got 4 key stages: intake, then evaporation, followed by condensation, and finally, collection of that fresh water. All right, let's trace the path. Seawater gets pulled in, some of it is used to cool those condenser tubes up top. The rest enters the main evaporator chamber, which is kept under that strong vacuum. Hot water from the engine heats it and it flash evaporates into steam, leaving all the salt behind. This steam rises up through a filter called a demister to catch any stray salt droplets. Then it hits those cold condenser tubes and instantly turns back into pure liquid. This fresh water, called distillate, gets collected and pumped to storage. It's just a continuous, elegant cycle, running all the time. Now, while the principle is the same, these machines come in a couple of different flavors. Most modern ships use a compact plate-type design because it's super efficient. Older vessels, though, might use a larger, more robust shell and tube type because they're built like a tank. So different missions, different designs, but the same clever physics is always at work. And this brings us to the real genius of this system. It isn't just that it works, but how incredibly efficient it is.
It is an absolute masterclass in turning waste into a vital resource.
I mean, here's the genius of it all. The fresh water generator takes something the engine is actively trying to get rid of, excess heat, and uses that waste to create fresh water. It requires almost no extra energy. So it's not just a water maker, it's a massive energy saver that even helps cool the engine. It's a win-win-win. And that really just captures the whole spirit of marine engineering. In such a demanding, isolated environment, efficiency isn't just a buzzword. It's the key to survival and sustainability. It's all about using every single bit of energy as smartly as you possibly can. So in the end, the solution wasn't about more power, but about a simple, clever shift in perspective. It really makes you think, what other impossible problems are out there right now, just waiting for someone to come along and change the physics?